My name is Lawrence Kearney. I work for the University of Georgia. I'm a system administrator principal there. And I have always been somewhat of a SUSE evangelist. I've never worked for SUSE properly, but I've always been kind of a member of Team Green. I'm also a SUSE certified instructor. I did my first course development for SUSE a couple of years ago. If anyone's been working with SSSD, I did write the SUSE SLE course, 342 for that. And I've been an HPC infrastructure specialist for about 4 years now. And primarily, I've not focused on HPC administration. I've basically focused on HPC deployment, design, and infrastructure decisions. I have a huge presence on the SUSE and OpenSUSE forums and on the SUSE blogs. And I will recommend that we have a lot of potential to go into a lot of depth here. I don't want to muddy the water, but there's a certain amount of high-level overview that we need to get through, I think, so the concepts become clear. And all of the technical procedures and instructions that I'm presenting in this tutorial, I have actually blogged about in detail on the SUSE site. So whatever we don't have time to drill into here, you can always go to the SUSE site and basically get the exact deployment that I'll be demonstrating here. And you'll be able to deploy that yourself. And if not, you'll have my email contact information, and of course you can contact me out of band. And I am also a motorcycle owner and enthusiast. I've had motorbikes my entire life, and for the past 10 years I've owned two. I've owned two concurrently, and it's hard riding them both at the same time, but I keep trying. So what we're going to talk about, we are going to do a cluster architecture overview, and that's kind of why I asked. There's a couple more people in the room. How familiar are we with HPC? Okay. And you work for a center, or? Oh, fantastic. Well, thank you for coming. I know this is going to be a little below your pay grade, but hopefully you'll glean something from it. If nothing, we've got these really cool Raspberry Pis running a cluster. So we're going to do a cluster architecture overview. We're going to do a deployment overview, a workload manager overview, and we're going to have some basic interaction with a Slurm-based cluster. And Slurm will be used for the workload manager in this particular cluster, and we'll drill down into what a workload manager actually is in just a moment. And we're going to, if we have time, we're going to look at some file system architecture stuff, because there's a lot of rabbit holes you can. What was that? Okay. Okay. There's a lot of rabbit holes you can go down. File systems are certainly one of them, but definitely necessary. And it's nice to get somewhat of an understanding of why there's so much flexibility and why there's so much complexity in file systems that are attached to HPC clusters. Oh, yeah, we'll just go right into HPC environments. Typically, from a system component point of view, you're going to have a head node. Best practice, you'll have multiple head nodes for redundancy, but for the sake of our conversation, we're just talking about what components go in what slots. Head nodes generally will run the intelligence for the cluster, specifically the workload manager. You will have compute nodes which can vary in architecture, which can vary in processor architecture primarily because of applications that utilize those platforms. You're going to have everything from Intel to AMD to GPUs and to ARM, which is currently actually running an HPC cluster here. Raspberry Pis are quickly bleeding into the data center because they're very low power. They're very cost effective, and it's actually a little easier. This is jumping forward a little bit, but there's less development involvement to convert scientific applications to ARM-based systems than there are GPU-based systems. Sometimes there's actually no code changes required. So it's quite a handy ecosystem and platform for HPC. For instance, with this one particular cluster, I've only got 6 nodes active because I wanted to bring my small switch instead of my big switch. But basically, I have in that package, I have an investment of about $450, and I have a 48-core system that I can throw some work at. And if you just have the right software stack to utilize those 48 cores, you can do some stuff. If you imagine scaling that out, and I'm sorry, this is not supposed to be an ARM commercial, but the University of Edinburgh recently did a parallel deployment of their Intel Skylake-based Archer supercomputer with ARM-based components, and for a significant reduction in cost, actually improved their computational capacity. So ARM in the data center in HPC, it's not very prevalent now, but the potential is becoming very apparent. That said, you also have compute nodes, which you can have 8, 16, hundreds, thousands. And that's another conversation in of itself, and we will absolutely get there. Your workload manager is basically your resource and job management scheduling. So computational work in HPC is broken down along job boundaries. So you've got an application that's available on the cluster. You're going to write a script to address a data set and an application to consume it, and throw it at the cluster with as many resources as you can, or as many as you can schedule, and go, let me know when the work is done. That could be seconds, that could be hours, that could be days, weeks, months. So scheduling the CPUs that are available, knowing which CPUs are available, knowing how much memory is available collectively in the cluster, knowing what jobs are supposed to end when. These are all parts of what's referred to as the workload manager, to actually schedule hardware resources and then manage the queue of work to actually start using those resources when they become available. And if you want to get into the technical bits, there's actually a component of scheduling called backfilling, which takes into account when jobs are supposed to end, how many cores are going to be available, and if there are resources on a node that can be used, it will attempt to schedule that work on resources that normally would not be available, as long as the jobs end when they're predicted to end. So a workload manager in an HPC environment actually is responsible for doing quite a bit of magic. And you have generally databases. You will rarely see a flat file-based systems for databases in HPC. And before we get into that, I want to tell you why databases are used in HPC. You have a fairly complex software configuration, potentially. Several of them. The database not only stores the configuration for those applications, but it also stores the configuration for the workload manager and the cluster itself. So basically, the workload manager will start. It will refer to a configuration file that will point it to a database that houses its metrics and configuration, and then load the applications. Load the applications that are the workload manager. Also, the database is used for storing metrics for what's happening in the cluster. How many CPUs are being used, how much memory is being used, job-based details. And that's a very important aspect of what the workload manager is doing, because as well as managing the work that's being done at the moment and the work that's going to be done in the near future, the workload manager also stores metrics for all the jobs that have run in the past, so that you can run reports against them and kind of gauge, do I need to scale my cluster? Are there not enough resources? Are jobs waiting too long to run? So that kind of metric collection in HPC is very important for trending and for scaling out HPC operations, making sure that they're fluent. And that's why I say you will rarely see that in a flat file. You'll usually have a relational database that can actually handle that kind of workload, because you can imagine what kind of data stream that is. And you'll also have some accounting packages to run reports, of course, against those databases. You will see flat files in smaller Sun Univa-based clusters, just to mention where you might see that. So you'll see that in test clusters, and you'll see that in smaller Univa grid-based clusters. And the Univa grid, is it still Univa grid? We've got some HPC people in here. Is it still Univa grid, or is it Sun grid now? Or do I have that backwards? Okay. Okay. That is another workload manager that's actually been passed down through a couple of different companies, including Sun, that have basically re-implemented it. I would not say it is prevalent, but you still see a bit of it out there. And at any point, interrupt me for questions. If my rate of speech is too fast, let me know. Because I know not everyone here, of course, are native English speakers all the time. So, your basic HPC job flow. So it starts with your researcher sitting in a workstation that has SSH access to a login node. And sorry, backing up to the components, you generally do not give access directly to compute nodes to users. They'll have actual login nodes. Sometimes the terminology will be used submission nodes, because what they're basically doing is submitting jobs. So they'll have access to submission nodes that have the ability to communicate with the workload manager and actually submit jobs. So our researcher will log into a login node. He will run his composed script using the binaries for the workload manager for submitting the script. The head node will then actually schedule that, run that job on compute nodes, and when that job finishes, according to how it's configured, then our researcher will get the results in whatever kind of data packages he's running the application against, or whatever kind of return set or data file that he's accustomed or he's packaging the results in. And that's basically, that's your basic HPC workflow. I get a data set, I get access to an application, I write a script to utilize them both. The workload manager hands it off to the compute resources. The job is scheduled, the job is run, the results are returned to the user, the resources used for the job are returned back to the compute pool. We were kind of touching on a little bit of this earlier, some additional HPC components, and I am going to watch time because I want to make sure that we get as much of this in as a proper introduction as we can. What was explained was a very basic HPC workflow. The truth of it is HPC, of course, is much more complex than that. You're going to need monitoring nodes. If you have a small cluster, the capability to monitor is not that imperative. If you have hundreds or tens of hundreds or thousands of nodes, then you kind of want to know what's going on all the time. One instance of monitoring is the paradigm with HPC compute is very different from administrative computing. So at the University of Groningen, when I visited their HPC center there, and I was chatting with their folks, there was a huge monitor up that showed the utilization for the cluster. And basically, it was constantly at 100%. And every now and then, you would see this little dip. And it would pick right back up. And what you want in administrative computing, you want everything below 50 so that you can handle the spikes. In HPC, you want absolute and compute utilization of all of those resources all the time, and a dip in efficiency is undesirable. So, and hence, once again, the importance of the workload manager. So you have to kind of shift your mode of thinking when you start talking about HPC as well. So metrics collection. Once again, if you think about why you would want to collect those and why you would want to trend those data, you want to know what the utilization of your cluster is. Like I said, your most obvious component is going to be jobs are waiting too long. Jobs are waiting too long to start. They will stay in a pending state. So that could be a job queue configuration issue. That could be a resource allocation issue. That could be a hardware availability issue. It could be a software issue. Unless you actually have those types of, unless you're collecting metrics on everything, it's hard to correlate exactly what the problem might be. But the most important reason I would say would be for trending the efficiency of your cluster and projecting use and capacity. Application delivery nodes. A lot of times, applications are put on slower commodity hardware. And we've all worked with storage enough to know that if the CPU is fast and the memory is fast, that's great. But if the storage is slow, then you will not get the performance that you expect. So with larger clusters, having dedicated application delivery nodes with those applications and especially databases. The one for your Workload Manager configuration store, and a lot of applications have ingress to databases as well. Putting all of those on SSDs for larger clusters is going to be, you do not want those slow disks to be your choke point. Application development nodes. Does anyone know where scientific software comes from? Anyone, take a shot. Yes. I'm sorry, did you not raise that? Oh, I called him out and he didn't raise his hand.
They all come from a long time ago.
Well, a lot of them do come from a long time ago, but I didn't understand until I went into research computing that why researchers had computer science degrees. Because the chances are the software they need to do their work and do their research does not exist. So in order for them to do the science they want to get done, they, more likely their grad students, are going to write the software. That's why you have this huge parabolic of efficiency and best practice with scientific software. Because these guys and women want to get the science done. They can't be bothered with writing a good Java stanza, you know that. So they more often than not, they write their software themselves. And so most HPC clusters will have application development nodes specifically for that purpose. And because you can have a plethora of architecture for actually running that software, more often than not, I'm not a programmer, so I don't want to speak definitively, but I'm pretty sure it's the case, you're going to have to develop the software you want to run on the hardware platform it's intended to run on. So depending on what hardware platforms you have in your cluster, you're going to mirror that with application development nodes that are made available to your researchers as well to actually write and build their software. Most times the case will be there are a lot of open source scientific software packages out there as well. It may just be a matter of getting the source and just building it on whatever platform you intend on running it on. So whether you're actually doing the development yourself or you're just building the software, these are still going to be key components. Data transfer nodes. Often overlooked. The other aspect of the paradigm of scientific computing is you are dealing potentially with incredibly huge data sets that are being sucked in to actually do the work. You know, if you're going to throw 600 cores and, you know, a couple terabytes of RAM at an MPI application to consume, you know, a 2 terabyte data set, that's a lot of computational payload, and chances are the output's going to be pretty large as well. And most of these researchers are collaborating with other researchers. So where they're getting data sets from and where they're sending data sets to are a pretty big component. So you are going to want dedicated data transfer nodes that are geared for just transferring these huge payloads either within the institution or the facility themselves, or of course across the internet, which likely, I'm hoping, only happens over an Internet 2-based connection. And also a data transfer node is going to be a component that is a stripped down version of an OS that's just there to transfer data. You know, you're not going to have the regular smattering of Linux utilities that are there to actually make Linux life easier. This server or these servers live for one reason alone: transfer large amounts of data from here to there. And a lot of times that happens on your own infrastructure as well. Segueing into storage nodes, you will also want your dedicated storage subsystems on very fast interconnects as well. Because I almost got ahead of myself. A lot of times you're going to be transferring these large payloads within your own infrastructure as well. So once again, the data transfer node being very performant is very important. Because if you're going to have on your very expensive scratch storage, which is generally this very performant storage that's used to actually compute against. So that's the actual storage that the compute nodes themselves have access to in order to actually do their work. Now, a lot of times, since that's very expensive storage, you're not going to want a 3 terabyte data set sitting there for months because it's convenient to leave it there. You'll want some type of nearline storage that matches the capacity that's not as performant, and a data transfer node that can transfer, that 2, 20, 40 terabyte data set reasonably fast off that storage and put it on cheaper storage. So those are all very important components to talk about, and I just kind of wanted to give a brief overview, and I'm watching my time. We're doing okay. And that takes us into storage, into specialized file systems. I won't spend a lot of time on this because we'll have an opportunity to visit this at the end if there's if there's time. But in the same way that there are specialized tiers of storage from a performance and capacity perspective, there are file systems that will take advantage of those performant criteria to actually provide the best services. Lustre and GPFS are two of the file systems that are very commonly used for direct inline compute. So you're going to put Lustre or GPFS-based file systems on very high performance arrays that have direct connections to your compute nodes, generally via InfiniBand. And that's how they're going to access that storage to actually do their compute work. When it's done, that's where the resultant data sets are stored. You'll want to put it on a different type of storage just to actually make room on the scratch storage and make sure that you have the facilities for that researcher to keep that data for a reasonable amount of time. And for the nearline storage, as I would call it, you will generally see ZFS being used. Has anyone used ZFS? I know that, yeah.
It's on Sun, isn't it?
Used to be Sun, yeah?
Yeah. Well, it's not Sun anymore.
Yeah. Very, very prevalent in Linux. You'll find ZFS available on Linux. I personally have a love-hate relationship with ZFS. On the yes?
EPFS is Spectroscale, right? Yes. Yeah, Spectroscale. Yeah, that's the old name.
Oh, was it? I did not know that. You learn something every time on both sides of the table. So, thank you. Spectroscale?
Spectroscale.
Yes, spectrum scale. Oh, yes, IBM.
Yeah.
Yes,
Right.
yes, that's right. Okay. So ZFS has the ability to aggregate an incredible enumeration of disks. It really does. That's its one capability. It is able to aggregate disks and provide file systems that have an incredible amount of depths. And if you've ever seen a research data payload or result set, you're talking about the potential for tens of thousands of subdirectories, sometimes more, with potentially millions of files in them, small, large. There are not many file systems out there that can handle that kind of metadata and that kind of file system semantics. ZFS is one of them. And it's very prevalent because it's free. It's been ported over to Linux. If you're getting into HPC, I don't see how you'll really get around it without using ZFS. My problem with ZFS is the lack of documentation. It's not .10 in the open source world yet, and as coming from an administrative computing background, that just bothers me. It's been out there forever. It's still a .9 something. But nothing else does what ZFS does, in fairness. And quite often, Lustre will be built on top of ZFS. So basically, the real claim to fame for ZFS, or one of them at least, is you have the ability to aggregate disks into what ZFS refers to as virtual devices. So what we would call a RAID. So you can aggregate disks into a VDEV, and then you can aggregate the aggregates and stripe across them. So that's part of the reason why ZFS scales the way it does. People will often refer to as ZFS subsystems as ZFS chains, because you can almost just continually just build on that model and add capacity. But with that capacity comes complexity. So the same way you might find it being very, very complex to manage 2,500 compute nodes at some point in the future, you might find it complex managing 2,500 disks in your ZFS subsystems. So that's the love-hate part for me. Oh, and there are specialized data transfer applications for managing those data transfers. One of them is Globus Online. You can certainly research them. They are pretty much the bomb in that space. And they're researchers writing software for researchers. So as far as having a GUI or a web-based application that researchers can actually use to just drag and drop large data sets from one part of the world to the other, Globus Online is really what you want to look at. And file system auditing, there's a couple of them out there. Robinhood is an open source project that's become very prevalent. But with those incredibly large data sets, you have an application that can basically mirror the metadata and run reports against it. So you can basically perform auditing features and stuff. Because when you have 4 petabytes of scratch, very expensive scratch storage, you're going to audit it because researchers will do, and like I said, they're about getting the science done. This is not about pointing the finger about, you have to kind of push the administrative, computing paradigm aside. You know, if it's convenient for them to leave their 40 terabytes of data on that very expensive Lustre storage, they will. It's up to you to provide them someplace else to put them. Well, to put it and to let them know how long they have to do it. So Robinhood can be one of those tools that's very handy for those types of metrics. And high-speed interconnects, we were just kind of talking about that. This is where this comes to bear. For all of the data transfer components that we were talking about, depending on how large your cluster is, what your budget is like, you can go all the way up to 100 gigabyte Ethernet, of course, for some of those interconnects. When you get to that point, whether it's better to do Ethernet or whether it's better to do InfiniBand is kind of a different discussion. You lose a little bit of, you lose some performance when you do IP over IB with InfiniBand, but it depends on what you actually have coming over your InfiniBand and how large the fabric is. And taking us actually down to the last bullet, what type of InfiniBand is it? You know, would you save money by implementing a new very high-speed Ethernet framework? So for instance, say to go to 40 gig on your Ethernet, and that will offload enough of the storage traffic from your existing InfiniBand fabric for it to be able to manage the capacity of the compute workload, and you can upgrade it in 2 years when the budget refreshes. So I mean, once again, that trending and metrics collecting, very important for making all of these decisions. And also, I'm mentioning Intel and Mellanox for a specific reason with InfiniBand, and with the switching as well. Mellanox switches are very prevalent in HPC. And this is another example of the difference between the administrative computing paradigm and the research computing paradigm is a lot of the Mellanox switches, which are geared towards life in an HPC environment, are what's referred to as a cut-through switch, if I have the terminology correct. So very little buffering. They're not worried about data integrity like your administrative computing switches generally are. You know, they're not going to look at the data as closely. They're just going to, their job is to get that data from there to over there, as close to line speed as possible. So they're going to throw away a lot of the integrity components that you would normally find in switches. So once again, it's a use case sort of choice. And also the Intel cards. We were, at the University of Georgia, we were running a TrueScale fabric with Intel cards. We eventually ended up merging the fabrics with a new Mellanox EDR fabric. And the acronyms for the InfiniBand flavors there are staged according to performance. So QDR being the least performant, HDR being the most performant. So we were merging our QDR Intel TrueScale fabric with our newly deployed Mellanox EDR fabric. And what we found is we had a remarkable performance beyond what could just be explained with line speed within the Mellanox environment. And it was determined that the Intel cards that we were using for their fabric did not do CPU offloading for processing the data. So basically, it was all left up to whatever the actual controller on the card could perform. Whereas the Mellanox cards did have CPU offloading, and they could not only process at their line speed, they could hand off some of that computational work, obviously, to the system and achieve more performance. So you want to look at all of these things, and I mean, ask yourself, whenever you're deploying anything for HPC, don't compare it to what you're used to doing. Always ask yourself, what am I trying to do? And that is going to make your researchers happy. And we will get to port density of your switches right now. This is typical. It's not as complex as it could be. But it gives you an environment of why not only with performance and actual getting through to line speed, you have a lot of connection density within an HPC environment. And it's halftime for our session now, so we've got 20 minutes after this. I will move through this very quickly, these next bits, because I actually want to get to some of the bits with showing you some of the bits of the cluster. So for hardware management, IPMI, iDRAC, ILO, whatever hardware platform you use, you're going to have a dedicated connection for that. Notice the head node has two. And generally what happens there is you have a dedicated IPMI connection for the head node itself, and the head node itself has a dedicated interface on the IPMI network so that you can use it to connect to other IPMI interfaces in the infrastructure, so that that's kind of your central ingress point for IPMI. Let's see, your login nodes generally going to be connected to your LAN. And potentially your 10 gig Ethernet, so that it has high-speed application to application storage. Now notice we've got we have a InfiniBand network, and we have a 40 gig network. Notice that the compute node is connected to them all, and we'll speak about the 40 gig in just a moment. The data transfer node is connected to them all. I mean, for obvious reasons, it may need to move data across all of those infrastructures. And the login node does not. Anyone want to venture a guess why? Because that is about the only thing differentiating a login or submission node from a data transfer node. And if your researchers can avoid logging into another system, they will. And when they bog down your submission node with the heavy workload of actually transferring those tens of terabytes of data, no one else can log in and submit jobs. So you want to differentiate from a network perspective your login nodes and your data transfer nodes. A Science DMZ is typically available at larger universities that have an Intranet 2-based connection. And the reason for that is you're transferring large data sets across the intranet. And your compute nodes may or may not have a connection to the Science DMZ, but it is possible to have compute nodes actually pull those data sets directly from the internet and work with them, or send them directly across the internet. Whether or not you do that depends on the security stance of a university and what your perimeter security is like, and how big of a research workload that your university has. And most of this, and so this being said, we're actually going to move through this very quickly, because I do actually want to get to some other stuff. Is that okay with you guys? Are there any questions so far? Okay, and I bring all of this up so that you have a high-level overview of what it's like in a mature HPC environment. Sometimes it's nice to see where you might be going before you decide to do a thing. Yes? Yes, yes. And I didn't mention that explicitly, but we actually opted for Mellanox over OmniPath when we actually upgraded our InfiniBand infrastructure at the university. And the nice thing about the sleep packages, yes?
So in the previous couple of slides, you mentioned about a cluster for compute nodes. So what is the typical size of compute nodes we are looking at? I mean, I have no clue.
The question was, what is the typical number of compute nodes?
Yeah, in a cluster, which
In a small cluster, you'll see between 16 and 32. In a medium-sized cluster, you'll see between somewhere between 64 and 256, thereabouts, and larger clusters are going to be generally greater than 256 nodes. And of course, if you have 8 or 16, if you have 8 or 16 cores per node, that's why supercomputers are rated in the amount of memory they have, the amount of processes that they can perform, and the amount of cores they have. So those are the metrics you'll hear for capacity with supercomputing. Let's see, you're going to need to connect to identity stores. You're going to need all the regular infrastructure services that administrative computing services do. And you're going to need a node deployment tool, because compute nodes are by nature disposable. The whole point about them is if something goes wrong with them, or if the hardware breaks, if the OS breaks, you just bring it out of the cluster, redeploy it, and just carry on. Let's see. We've already talked about where HPC applications come from. You may also need custom software repositories. You have a lot of scientific application dependencies, and a lot of file system driver dependencies that may need to be met. So you may want to control the versions of the kernels and the things that are pushed down to compute nodes to make sure you don't break these things. So it's just a matter of version control for the OS components. And so back to workflow. And basically, the reason why we're back here is because wouldn't it be awesome if starting was easy? And that's kind of where I wanted to get. Did I break that? Or is it just going very slowly? Oh, there we go. So one of the biggest advantages of deploying HPC on SLE is it's easy to deploy, it's easy to configure, and it's supported. It really is a fantastic way to start digging your. It's really a fantastic way to start digging your claws into HPC if you've never done it before. And once again, the instructions and the procedures I used for deploying this ARM-based cluster are on the SUSE blog site. So just search for Lawrence Kearney and you'll find them. So it does begin with the SLES Unified Installer, especially with SLE 15. You simply select the products, the extension and module selections you want to use. You select the system roles, which we've already discussed for whatever system you're deploying on, and then you do the configuration and testing. And it really is very straightforward. Knowing what we've discussed now, these screens should be fairly self-explanatory. You're simply going to choose a node. You're simply going to choose a node pattern, and you're going to deploy the software on it. And that, of course, is the easiest step. For compute nodes, you want a minimal OS, because it's just there to compute and do nothing else. Modularized libraries are a way of modifying an environment to run a particular version of a scientific application. The most prevalent is called LMOD for load module. So you basically have the ability to load a particular environment that an application expects, usually a specific version, and then run the application inside of that environment, even on the compute node. It's kind of container-esque, might be the best analogy to throw at it. But it's basically providing a specific application with a specific environment for a specific workload. And it's referred to as loading modules. And I just wanted to be clear with that. Different from, of course, SLE modules, which are installation patterns and components. Login nodes, once again, you want a minimal OS, but you'll want some of the Slurm utilities on it for users to run and do things and to interact with the cluster. Data transfer nodes, once again, minimal OS, very sparse utilities. It's there to do one thing. Basically, your development nodes are going to be more complex. They're going to have a more complete OS. They're going to have modularized libraries as well as development tools. And partitioning, we'll just move right past that. These are just the default partitionings because I want to make sure we have time. And so we have the product this is just an installation summary for the Workload Manager, compute nodes, and for the development nodes themselves. So daemons. We're actually going to start, no, we will start at the top. The Slurm control daemon is the actual Workload Manager itself. The Slurm database daemon manages the configured database that was installed with the software when you installed the Workload Manager packages. And the Slurm daemon itself is the actual daemon on the compute node that executes the jobs. Best practices, you'll want primary and secondary nodes for the control daemons. Failover, obviously. You'll want dedicated SSDs for the database, and you will want to implement the pluggable authentication modules for Slurm-based compute nodes. In short, what the PAM modules do is, what you want to do is prevent researchers or users from logging into compute nodes and just doing work out of band of the Workload Manager. So the best way to do that, there are many ways to do that, but Slurm provides a utility that is actually really cool. They provide a PAM module that will not let a user log into a compute node where they do not have a job running. So it's kind of like the best of both worlds. So you'll want to actually give them access to the nodes running their job in case they need to tweak something or do something else. And the additional benefit of the PAM module is if they do anything out of band of the Workload Manager, those metrics are captured as well. So if they submit additional work on that node that wasn't included in the original job, then it gets recorded in all the metrics databases as well. Your slurm.conf pretty much goes on every node in the cluster except for the database box. So it's the unified configuration for everything. This instance uses MariaDB, and the Slurm database daemon is configured to use the Maria database that was installed when we installed software stacks. So this is a list of the things that you basically need to configure. We're going to move through this pretty quickly because I want to go ahead and show you the cluster. Your configuration file placement, as I mentioned, pretty much a copy of the slurm.conf goes everywhere there's a Slurm component running. And in the case of the login node, even where it's not running, because some of the user utilities will need to reference it in order to connect to things in the cluster. And let's go ahead and start the cluster. Let's just do that. I brought my glasses, so there's a chance I'll be successful. So let's see. We are, and I hope everyone can see that well enough. Yeah? Well, except for me, apparently, actually. Well, this is going to be hard. So let's start. The order of start will be, this is the head node. So we're going to start the database. We're going to start the database daemon. We're then going to start the control daemon. And let me actually see. Let's see if I can work off of one monitor. How about that? Because that would be better. That way I'm not constantly looking over my shoulder. And we'll just do it this way. There we go. Yes, we can both see. Fantastic. So we'll start the database. We'll start the database daemon. And we'll start the control daemon. Now, we have a running cluster at the moment, but with no compute nodes. And I've got all of the commands in the slide deck, so even though we're kind of going through this section pretty quickly, everything I'm doing is captured in the slide deck, which you'll have access to, and of course, in the blogs that are available on SUSE.com. So, right now, I have cluster awareness, but I have no compute nodes. there is a utility, and I'm actually going to do a blog. This is a blog coming. This is a blog entry coming very soon, probably the week after SUSECON. You have the ability to use a parallel utility that can target all of the compute nodes and run commands against them in parallel. So that's what I'm using here. So what I'm going to attempt to do is start all of the daemons on four of the compute nodes. And I do not actually have the other two connected, so that's why I'm getting that information back. So if I have a look at the cluster now, there we go. I've got 4 nodes which are idle. And of course, four CPUs each, how much memory I have on them, and they're currently not doing anything. So let's go to the login node, and I'm currently logged in as one of the researchers in my cluster. Ming Steele, she's secretly a superhero that does supercomputing in her spare time, apparently. And she's going to run a job. And one of the Slurm utilities that the login or submission node will need to have is sbatch, which is what a user would use to submit a batch job. And that utility needs to be able to read the slurm.conf in order to be able to target, well, for instance, who is my workload manager? Who am I going to send this information to? However, what you do not want on the submission nodes, even though you will install the Slurm package on it, you don't want the systemd scripts for starting daemons or for doing account management. You would strip all of those utilities out on a submission node. So let's go ahead. Well, first of all, let's have a look at this. Let's have a look at the script. Oh, well, I did say I wasn't an administrator, right? So pretty straightforward. My job name, what partition the job is going to run into, and partition is synonymous with the term queue. So basically there are configured queues waiting for work. This is which queue I want to send this job to. And the concept of queues is important because queues are associated with compute nodes. So if I have an application that's supposed to run against GPUs, I would want to submit it to a job queue that had GPU nodes assigned to it. If I had a job that required a lot of memory, all of my compute nodes are not going to have 512 gig or a terabyte of memory. I'm going to have 4 of those. Yes?
Does Slurm support checkpointing?
Yes, it does. Yes, most HPC workloads do. Yes. So the short answer is yes, absolutely. And checkpointing is the ability of, I'm sorry, the question was, does Slurm support checkpointing? Yes. And for those that don't know, checkpointing is the ability to periodically take a snapshot of compute work being done. So if something happens to interrupt the job, like a node crash, which with grad students writing applications certainly happens.
Or if you're backfilling.
Yes, yeah. Exactly. Your job can pick up at the last checkpoint. And that's really important. If your job's run for seconds, you don't care. If your job's been running for 6 weeks, you care. Yes?
And what level does it do checkpointing by itself, or does it require the application?
I believe it requires some configuration. Now, checkpointing is often a feature of applications. I would actually go so far as to say that Slurm itself does not implement the checkpointing, the applications do. That is my understanding, but I can certainly be checked on that.
So
Yeah.
I'm not sure what it means for Slurm to support checkpointing. It's not the application.
And that's a fair point. There are, I
You
think,
need to tell the application to checkpoint.
yes,
So if the queuing system doesn't support it, it will.
just ignore it. Yeah, yeah. So if the workload manager doesn't support checkpointing, it doesn't matter if the application tells it to checkpoint. And you might also have high memory nodes, of course, if you've got a job to submit and run directly against those. How many CPUs to use, how much memory to use, what's the maximum amount of time for the job, and as we were discussing before, where to put the output, and where to put the error information if it crashes, and the actual work I'm going to do. So this is just a little script I've run that does some random number stuff, writes it to a file, and then sorts it. So just a basic script that's actually going to run in the cluster. If I look at the queue at this moment, then there's nothing running in the queue. And once again, partition in Slurm parlance. If I go ahead and run the job, and I'm actually going to run a different one. So it lets me know it submitted the job, and if I look at the queue now, then I do in fact have a job running. It's running on node 1. And if I look at my nodes, I see that node 1 does in fact have work going on. And the state of mixed means basically I have some compute going on, but I have other resources available. So it could be, it's saying that there could be mixed workloads on this node. There are instances where the core density in compute nodes gets to be more problematic than beneficial, depending on how granular the configuration for your workload manager is or how savvy your staff is. Because if you mix workloads on a node and one of them is using a very poorly written application and crashes, well then all jobs running on that node have been lost. So some administrators will take the stance that no matter how cores are available on a node, they'll only allow one job to run on a node. So I hope that helps kind of explain that the mixed here makes a little more sense. And if you actually go to the compute node, you should see Ming's job work up to the top there at some point as Slurm script. So that's what the system refers to it as, because the job was actually executed by the daemon running on the node, but the ownership of the job is actually Ming. So all the metrics and all of the results and the files created will still be owned by POSIX standards by Ming. So that is, I mean, it's a functioning Slurm-based cluster, and it's really nice, and that's why I wanted to bring it. It takes me entirely too long to set it up. I don't know what I'm going to do tomorrow. I had an hour to come in here and do this, and it took me 25 minutes. So I don't know what I'm going to do tomorrow because I'm coming in between two sessions. And that said, let's go back to the slide deck for a moment. There we go. And let's just actually, I'm going to have to close that for the moment. I'm sorry, let me pause for questions, actually.
So the input and output management, like in the script, there was some input and some output. Mm-hmm. This is all handled by Slurm?
Yes, it is.
It's all managed by Slurm?
It's all managed by Slurm, yep.
So the input directory, which you specified, and the output directory, so the syncing of putting it on all the compute nodes wherever the job is scheduled and then bringing it back.
Exactly. And the file systems referenced in the script obviously have to be accessible to compute nodes. So you have a lot of mounting logic that you need to make sure that you think through. And it's not, I mean, that part of it really is not very complex. I just have a little NFS server running on one of these Pis that just basically is serving out 3 different file systems, one for home directories, one for job results, and one for actual compute. So really, that's all you generally need to actually perform those tasks, at least to get started. And I will very quickly, oh, yes. Oh, sorry. And I'm going to go ahead and take these nodes down. I'm going to try to be friendly for the folks that are coming in the room after me and not damage my cluster so that we can use it tomorrow as well. So I can stop, ooh, and I stopped those while a job was running. I hope I checkpointed it. Chances are the little script I wrote that ran some commands doesn't checkpoint. So I've just, as we say in the HPC world, lost my job. And we're going to stop everything in the reverse order. Let's see. And all of the Slurm packages that were installed were just installed right from the unified installer. I simply chose Compute Node, Workload Manager, and the form to actually do the common method for generating the configuration file that you can start with is a web form that you can either go out to the Slurm site and use the online version. They have an easy web form and then what they call a complete web form. And you simply fill out the web form for how you want the partitions and what compute nodes are assigned to which partitions. You click submit, it generates your slurm.conf, and that's what you push out to the nodes. So, yes?
I'm curious, does the SUSE HPC module support stateless nodes?
Tell me what you mean by, I'm sorry, the question was, does the SLE HPC support stateless nodes?
So that disks, nodes do not need to have the operating system, basically including over the network.
That is not really a function of SLE. That's really your node deployment. That's really your node deployment capability. And what you're talking about is what's referred to as a Beowulf style cluster.
Yeah.
Do I have that right?
What is I thought the HPC module was doing the deployment. HPC, is that not incorrect?
That is incorrect, yes.
Something was deploying compute nodes.
In this demonstration, no. The compute nodes were already provisioned. I just started the daemons on them. And what the gentleman's referring to is a Beowulf-style cluster where one of the largest benefits of a Beowulf-style cluster is you get your arms around preventing configuration drift. And what happens is the head node actually has an image of software. And it actually will deploy compute nodes via PXE or whatever mechanism that you have. So when you power on a compute node, the head node actually deploys a software image, configures it, updates it, brings it up as a compute node. When you power that node down, or or by whatever criteria you set to redeploy it, the head node actually redeploys it from the configuration, from the image that it has. That's referred to as a Beowulf-style cluster. Slurm itself is just a workload manager. So so you would need ancillary stacks in order to actually automate that type of node deployment.
So what is the HPC module?
The HPC module is basically it's the ability to deploy Slurm compute nodes, the Slurm the Slurm execution stack for compute nodes may be a more correct way to say that. It's a way to deploy the Slurm execution daemons on compute nodes. It's a way to deploy the Slurm workload manager and to configure the workload manager. And it's a way to deploy ready-made HPC environment libraries so that applications can be plugged into them and run. So that is, in essence, what SLE HPC is.
So do you know what the benefit of using that over something like OpenHPC would be?
Primarily the support. And most folks new to HPC, everything that's done in these HPC packages and modules, there are several open source components to use in order to implement them and to augment them. But if you're new to HPC, even if you're not new to HPC, reducing the complexity of getting a working cluster off the ground quickly is the point of the SLE HPC modules. And that's why I started at the beginning of the session with all of the complexity, because it depends on where you want to go. But the SUSE HPC modules makes getting started easy. Does that help? Yes.
Just out of curiosity, what did you use in your cluster to deploy the operating system?
SUSE Manager. Yep, SUSE Manager can do bare metal deployment, and yeah.
Does it support like license metrics? You can send to the, when you submit a job, it will take like 10 licenses or don't overcommit.
The licenses for the HPC components are bundled differently.
So I think for the applications you're running,
Oh,
because if you run a commercial software, you often use some sort of floating license.
yes, and there are out-of-band license management components that you would need to implement in your stacks to actually do that. It's not uncommon to have. I don't like seeing it from time to time, but you'll see often a professionally developed scientific application will have a license manager server component. That's a one-to-one relationship with the application. You will find that. What is most prevalent in the open source community is having a license manager server, and you manage multiple licenses concurrently for applications running in the cluster with that one component.
Because you, for example, if you start a big work, you must be assured that you have licenses when you start, because otherwise
Yes,
it's lost.
exactly. Yep.
I had a question. You had a slide up there about the Mellanox fabric at one point. Is that supported right out of the box for the SUSE HPC as part of the module?
Yes, it is actually. Yep. Yep. All of the OFED stuff for InfiniBand is there.
Thank you.
You're very welcome.
Have you ever tried LSF?
No, not yet.
Because it's
Well, thank you guys.
okay.
Do find me around. Thank you.